Yes, dear viewers, we'll be back from the break. Before now looking at the general wave motion, before categorizing waves into mechanical and electromagnetic as per our topic outline, we need to first go back to the definition of wave. In the definition of waves, we have seen a disturbance in media bringing about transfer of energy. We want to see how this transmission of energy is done by a wave. This is what I'm trying to put here. We are saying that when a stone, we are giving an example. I told you to get your palm and punch it on the surface of water. But if that is difficult for you, we can go and get a stone and drop it in still water, water which is calm, okay, in still water. Then we are going to form what we call ripples. Ripples are going to spread out. Things of this nature are what we call ripples. We shall have things of this nature. Okay, those are ripples. Starting with very, very small in that circular form, they are going to spread out, and that is their direction. That is the direction of motion of the ripples. So, ripples are going to spread out in form of concentric circles. Concentric circles. And that's what we are going to experience practically. You can go and do it. So, from the point where the stone enters the water, from this point, assuming this is the water, from the point where the stone enters the water, we are going to form. You can even see them this side, spreading again this end, or these ends. And in so doing, they are going to form what we call concentric circles. So, what happens? So at the point where the stone enters the water, and if a floating body, if you get any floating body, for example, sponge, we can get sponge, and we place it in the ripples, where ripples are moving, okay, we are going to observe it moving up and down, up and down. So therefore, the molecules of water are moving up and down with the energy. They have acquired the energy, okay, which energy has been received from a previous molecule, and in so doing, energy is transferred to the next molecule. So that movement of up and down, we call it oscillation. So what do we mean by oscillations? Oscillations, we are going to talk about them as flow, the to and fro motions, to and fro movement is what we call an oscillation. So there is a need to talk about oscillations. So an oscillation is a to and fro movement. An oscillation is a to and fro movement. Take a look at a spring which is clamped, assuming you have a spring. And on this spring we attach a mass. Okay, an experiment which was done by Robert Hooke. If we attach a mass and try to displace this mass, pull it a little bit down and leave it to move freely, it is going to oscillate, a to and fro movement. It can be about a mid position, or what we call an equilibrium position. So we can also define an oscillation as a change which keeps on repeating itself regularly. You can as well define an oscillation in that format, because we have seen a spring. You have caused a change in the spring and it is repeating itself, okay, regularly. So an oscillation can also be defined as an oscillation is a change in a medium, okay, that keeps on repeating itself. That's what we call an oscillation. For example, when a watch or a clock rotates, that is an oscillation. It is performing a particular oscillation. A swinging bob. You have ever seen a bob? A string attached to a metallic spherical body. If I displace this, I displace it to this point, and then I leave it to oscillate. It will come to this end, and then finally come to this end. So it is a to and fro movement. A to and fro movement. So a swinging pendulum bob is an example of an oscillation. Some of the objects which produce oscillations are the swinging pendulum bob. A mass on a spring when pulled and released. I also gave at the preamble, I gave you a rope. When I tie a rope at one extreme end and then I swing it, okay, fixed at one end and then jacked at the other end. We can put those ones down for people who are making notes. The reason why I'm writing on the board is specifically for those people who are making notes, who are not going to have access to this work on video always and always. Electricity might be missing, but you need to revise. So you can put this work in your book. Just a matter of timing. When I've given you a very good posture, pause or make a screen printout. Control button and then print screen button. Then you can paste into a Microsoft document. A Microsoft document. That is a Word document. And then you finally keep those notes. Or you write them in your book. So examples, e.g., a pendulum, a swinging pendulum. A swinging pendulum is an oscillation. Swinging pendulum. You can talk about, we have said a mass. A mass on a spring when displaced. When displaced, a rope fixed at one end and jacked at the other end. There are many practical examples of these oscillations. Why am I talking about oscillations? This is the origin of wave motion. The origin of wave motion. Transfer of energy. We have seen musicians like Michael Jackson, okay, demonstrating this transfer of energy, the different strokes. Look at now how the energy is going to travel, okay, into my body. Look at this, a stroke, a stroke, energy, a stroke of energy now trying to flow into my body. That's what we are meaning by a wave motion. Transfer of energy, okay, but the medium, the energy is transferring. It's being transferred into the medium, but the medium itself is not moving. It is not permanently displaced. It is now just the energy which is moving through the body. So that is a live example. So immediately after a break, I'm coming back with the real introduction of wave motion. We want to see those categories: mechanical waves and then electromagnetic waves. Immediately after a break, we are going to be together. Yes, dear viewers, we'll be back from the break. Now we are on wave motion. We have started with the real wave motion. We are going to see that wave motion is divided into two categories. I.e., the first one is what we call the mechanical wave motion. Mechanical wave motion. And then we have what we call electromagnetic wave motion. So dear viewers, as you hear the word mechanical, mechanical. We are going to see that here wave motion is by a mechanism of transfer of energy through a medium. That is mechanical, through a medium, through a state of matter. All what I've been talking about here is about mechanical wave motion. Through a material medium, whereby particles are going to be temporarily displaced, but again they return back to their original position. And we are going to see that this mechanical wave motion is going to be categorized into what we call the transverse and then the longitudinal waves. In other words, progressive waves, they are going to fall under this mostly. Okay, so a major thing to note here in the mechanical wave motion, that a material medium is required. A state of matter is needed, either a solid, a liquid, or a gas, which is totally different from what we call the electromagnetic wave motion. Okay, so we can go and say that mechanical waves or mechanical wave motion is the mechanism of transfer of energy from one point, by a wave from one point to another, which requires, or in a given medium, or which requires a material medium. So I told you, when I talk of medium, think about a state of matter that is single. When I talk of media, the states of matter, media, it combines. Okay, so medium. So a mechanism of transfer of energy from one point to another, which requires a material medium, is what we call the mechanical wave motion. Somebody can ask you to define a mechanical wave. That a mechanical wave is the one which transfers energy from one point of a given medium to another. So what we can add here on mechanical wave motion, that particles of the medium are temporarily displaced, but finally go back or return to their original position. So particles of the medium are temporarily displaced, but return back to their original position. That is very, 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 very true. That is all about the mechanical wave motion. Now, what about the electromagnetic wave motion? Electromagnetic wave motion. We are going to discover that electromagnetic waves are made up of electric and magnetic vibrations of very, very high frequency, electric and magnetic. These ones do not require any material medium. We don't need a solid. We don't need a liquid. We don't need a gas for transmission or for the exhibition or the achievement of electromagnetic wave motion. What we need is electric and magnetic vibrations of high frequency. So we can note that electromagnetic wave motion, is the one that involves magnetic and electric vibrations of very high frequency, of very high frequency. That is about electromagnetic wave motion. We are also going to see, or we can add, that such waves or such a wave motion does not require a material medium for transmission, meaning that they can even travel through a vacuum, a space without any state of matter. So, electromagnetic waves. Electromagnetic waves do not, underline this, do not require a material medium. They don't need any state of matter, a material medium for their transmission. Full stop. So therefore, they can travel through a vacuum. Vacuum is single CW, through a vacuum. That is the interesting bit of electromagnetic waves. For example, those who are watching me live right now, from where you are, it's just because of this method. I mean, this wave motion, the electromagnetic wave motion. We are going to talk about what we call the electromagnetic spectrum. It is a combination of many waves. We shall see visible light is inside the electromagnetic spectrum. We shall see radio waves, the microwaves, the infrared radiations, the ultraviolet, but all of them are of varying frequencies. How are they produced? They are produced by oscillating electric sparks and very hot bodies. We need actually to talk about that. That they are produced by oscillating electric sparks. Oscillating electric sparks and very hot bodies. For example, the infrared radiations. So they are going to form different bands. Since their frequency, we shall talk about what we call frequency. Since their frequency is varying, they are of different frequency. Frequency is regarded to energy. When somebody talks about frequency, then what runs into your mind should be kinetic energy. So at this juncture, talk about their energy. The energy is so great, and it is differing in their category, because we have many under this category. So their frequency is going to vary. Now, immediately after a break, I'm going to give you some examples of these electromagnetic waves, and then finally we get a table giving differences between the mechanical waves and then electromagnetic waves, since that is a very, very good examinable area. They normally examine it. They normally ask for the differences between mechanical waves and electromagnetic waves. Don't miss that. Immediately after break is what we come in for. Dear viewers, we'll be back from the break. It is still your teacher, SULAIT. So we are continuing with our waves slowly by slowly. Now we have established wave motion in two forms. That is the electromagnetic wave motion and then the mechanical. But people need to know some of the examples. Before we give a clear differences between these two, what are the examples of mechanical waves? And what are the examples of the electromagnetic waves? So you can note, those who are making notes, note this and say that examples of mechanical waves mechanical waves. The ones which need a material medium for their transmission or propagation. How can you state them? The first one is, okay, we have the sound waves, that is good. Sound waves. What else? Yes, you can talk of the water wave, the water waves, that is good. You can talk of string waves. A string is different from a spring. So string waves and then the spring waves. Spring wave. And these are two different, waves. The spring and then the strings. So you can call them waves in strings or waves in springs. So those are some of the examples of mechanical waves. Waves which require a material medium. Sound cannot be heard if there is no material medium. My talking right now is enabled, is enhanced by, a medium. When I say bow, I'm setting molecules around my mouth also to vibrate in that manner, a manner of bow. That's what we are trying to talk about. So, material medium is very important for mechanical wave. Now, for electromagnetic waves which do not require any material medium, they don't require any state of matter for their propagation. Some of the examples are here. So, examples of electromagnetic waves. Okay, so the examples of electromagnetic waves are, okay, you can talk of what we call the gamma rays. Gamma rays. These are radiations. We shall talk about them in details under the concept of modern physics or nuclear physics or what we call atomic physics. These are radiations. Then we have X-rays. X-rays, we shall also talk about them in the same area of atomic or nuclear physics. Then we shall talk about what we call visible light. Visible light. Or what we call light waves. Light waves. They also don't require a material medium. Light can pass through a vacuum, can pass through any medium. They don't require material medium for their transmission. Those are light waves. Then talk about what we call the ultraviolet rays or ultraviolet waves. Then talk about the infrared waves. Infrared waves or radiation. These are also radiations. So we shall see that the sun can emit both ultraviolet and infrared, but at different intervals of a particular day, as we shall see with time. So infrared radiations, mostly by very hot bodies. Okay. Then talk about what we call the microwaves. Microwaves are also examples of electromagnetic waves. Then lastly, we can talk about the radio, then plus TV waves. Radio waves. Actually, the TV waves are also regarded to be radio waves. So instead of putting TV waves, we can just leave them as radio waves. So radio waves. Very interesting. So hope people have got this. Now, with time, we shall add on what we call electromagnetic waves. After now categorizing electromagnetic waves and putting them a particular type of waves, which we are going to call transverse, which are progressive waves, then we shall talk about the arrangement of these electromagnetic waves in what we call electromagnetic spectrum. So my encouragement is go and look for what we call electromagnetic spectrum. You make some research about it. Now, from this, we can go and talk about the differences between mechanical waves and electromagnetic waves. So differences between mechanical waves and electromagnetic waves. So once an examiner talks about difference, we differentiate by drawing a table of distinguishing characters. We put one distinguishing, okay? We can put one quantity on one side and then the other quantity on another side. So we can put the mechanical waves here and then finally put the electromagnetic waves.